Today we're going to talk about congruence by rigid motion. Rigid motions are transformations that don't affect an object's shape and size. That means that the corresponding side lengths and the corresponding angle measures of the pre-image are preserved when we move to the actual image. Translations, reflections, and rotations are all examples of rigid motion transformations. Dilations, on the other hand, are a change in the size of a shape. Dilations can be a reduction if the shape gets smaller, or an enlargement when the shape gets larger, right? In a dilation, all the sides are multiplied by a scale factor. If the scale factor is larger than 1, we're going to get an enlargement. An example of that is if I take the pre-image and multiply all the side lengths by 2. That would give me a larger shape that's double the size of our original pre-image. If the scale factor is between 0 and 1, like 1/2, that would give us a reduction because our side lengths would become half as long as the original pre-image. And because the side lengths change in a dilation, this is not a rigid motion. Two shapes are congruent if they're exactly the same, absolutely identical, having the same side lengths and angle measures. Congruence by rigid motion, then, is if we can show that one object has gone through a series of rigid motion transformations that map the pre-image onto the image. Let's take a look. In our first graph, we've got two objects. Be very careful to determine which one is the pre-image and which one is the image. And we need to decide what transformations have taken place. It's very obvious that these two shapes look identical. We're just going to verify. To do that, first note that both objects have the same orientation. That means that the image has not been rotated or flipped from the original image. That means that we've got a translation on our hands. Now I need to look at what type of translation took place. And to do this, I'm going to actually pick one vertex. I'm going to pick point B and look at the translation from B to B prime. And this looks like we went to the right 8 units and up 7 units. And I can verify that same translation for A and C and D to make sure that all the points got translated the exact same amount. Well, if that's the case, I can go ahead and say that these shapes are congruent, shown by the translation right 8 and up 7. Looking at our second example, if you look at the pre-image and the image, you can see that this shape has actually been flipped, right? This is a reflection. So we needed to determine what type of reflection took place. If you notice that point C is equidistant from the x-axis, or has the same distance from the x-axis as C prime. B is the same distance from the x-axis as B prime, and the same for points A and D. That means that we have a reflection across the x-axis. And if you verify that for every vertex, we can say the shapes are congruent. So my final statement could be something similar to, the shapes are congruent because the pre-image has been reflected across the x-axis. On to our next graph. This is an example of when more than one transformation has to take place to map my original pre-image onto the final image. So there's a few different ways that I could do this. There's not one right way and one wrong way to do this. There's probably several different correct transformations, but I'm just going to show you one. If I take my pre-image and I reflect it across the y-axis, you can see that I get a very similar shape to my final image. As a matter of fact, if I take that reflected object and translate it down 9 units, I get my image. So I can say, and I can verify that for every vertex again, I can say the two shapes are congruent by a reflection across the y-axis and a vertical translation of 9 units. Or I could say we translate it down 9 units. Either way works. These two figures are a little bit more difficult to tell whether they are congruent or not. Take just a second to look at the pre-image and the image and see what you think. Well, it turns out they are congruent, and I know that some type of rotation has taken place, but the rotation was not one of the ones we discussed in our previous lesson. This has not been rotated around the origin. So all I can say is there's some sort of rotation. And again, it's a little difficult to tell if these are absolutely congruent. So there's a little bit more we need to do for this problem. We can actually check for parts of our congruency by identifying all the side lengths, and I'd probably have to use distance formula to do that. And that's going to help us decide if the shapes are truly congruent. If all 4 corresponding side lengths are congruent, then I can pretty much say that the two shapes are congruent. So if I use the distance formula and find that the length of AB is the same length as A prime B prime, BC has the same length as B prime C prime, and so on, then I can say that the shapes are congruent. And my final statement would be something like, the two shapes are congruent by a rotation, even though I don't know what that rotation exactly is. In our final transformation, it's pretty obvious to see that these are not congruent shapes. They're similar, right? They are exactly the same shape, just one has been enlarged. So to state that two objects are not congruent, I only need one side length or angle measure in order to prove my conclusion. So I'm going to find a side length in my pre-image and in my image that correspond to one another, like AB and A prime B prime. If those two side lengths are not the same, then I can say for sure that the objects are not congruent. And I think that we'll wrap up our lesson for today. I hope your day is fantastic, and I'll see you next time.